And thank you, everybody, for joining us today. Today we welcome Dr. Tannaz from the university, the Teesside University in the UK. So Tannaz is there a senior lecturer in petroleum engineering, and she's also a chartered engineer in the UK and a member of the Institute of Materials, Minerals and Mining. Tannaz research focus on many subjects, including groundwater cleanup, water purification, hydrocarbon recovery, nanotechnology, soil remediation, waste management, but also sustainable material and non-destructive testing. She completed a PhD in 2015, and it was a PhD in geoscience at the University of Edinburgh in collaboration with the Heriot-Watt University, which is also in Edinburgh. Much of her research and today's talk is focused on understanding the dynamics of multiphase fluid flow within porous media at the pore scale. So, Dr. Pak, thank you very much for being with us today. We are looking forward to your talk, and if you would like to proceed, the screen is yours.
Thank you very much. Thanks very much, first of all, for inviting me. And I'm really happy to be here. It is really, it's difficult times, and we've all been away a little bit from doing research the way we used to do. So it's really a pleasure to give this talk today. So first of all, I want to acknowledge the contribution of all my collaborators and colleagues, and also the support that we've received from the funding agencies that I've included all the names and logos here, but I really have enjoyed working with all these fantastic people over the past 7 years. So this is hopefully going to show all of the results of in 2 specific studies that we have done, and lots of this comes from the collaboration that we've had together. So specifically today, I'm going to start from just setting the scene, giving you a very brief introduction on the subject area that I'm going to talk about. Then I'm going to briefly talk about X-ray computed tomography as the main technique that I apply in my research in these 2 specific studies that I'm going to present today. Then I move on to briefly talking about these 2 case studies. I selected these because I thought it would be nice to present a case for using nanoparticles, in general, reactive or non-reactive nanoparticles, to impact and influence on a distribution of fluids, multiphase fluids in porous media. So these are the cases, these are the studies that we've published in the past. In one of them, in the first one, we used non-reactive nanoparticles. In the second one, we moved towards having a more reactive nanoparticle and reactive transport. And we wanted to understand how that might impact fluid displacement in porous media. So the first thing that I want to show, if it's a little bit fiddly today, my mouse, but hopefully it will behave. So the first thing is that I wanted to set the scene in terms of explaining the context. So a lot of what I study basically has application in, first of all, producing hydrocarbons from subsurface, hydrocarbon reservoirs, and also there is basically quite a lot of application in other technologies such as carbon capture and storage. More recently, we are interested, at least in the UK, we are very much interested in using hydrogen as the future fuel, a clean alternative fuel for the future. And we are now studying storing hydrogen subsurface in depleted oil and gas reservoirs as well as aquifers. So this also will have application in that area, but also another main application for my research is groundwater remediation, trying to look at how we could basically clean groundwater that is already contaminated, and hopefully these examples will give you an idea. So I always start from explaining what capillary trapping is, because it plays a main role in all of the discussions that we are going to have. So I start from explaining capillary trapping, and I always use these images that I have borrowed from Wilson et al. So these are images of micromodels. So micromodels are simple two-dimensional network of capillaries, obviously transparent. We've started using this in order to study what happens to multi-phase flow in porous media. So if you want to do that, you can basically take a pattern like this, initially saturated with, for instance, oil and water. Here, oil is in black. And you can start to, if you want to study how effectively you can remove the oil, you can start, for instance, by injecting water from the bottom. You'll be able to produce a proportion of the oil that was in place in the beginning. But at some point, you'll realize that there's no more oil is moving. Everything that is remaining is actually trapped and trapped under what we call capillary forces. Now, you can start to think about how to target that remaining oil and remove it by thinking about basically influencing a number of parameters that are controlling this capillary trapping. And those include, for instance, looking at the wettability of the system, looking at the geometry of the system. If you're designing a porous media, you're looking at the interfacial properties of the fluids that are stored within that porous media. So there are a number of factors that are playing a role in on the extent and on the pattern of this trapping. So this is one of the main targets that I look at in different applications. So in order to study what actually happens in 3D, moving forward from micromodels and the simpler cases, now we have access to non-destructive techniques. Especially in recent years, we've in the recent decade, we have been able to use X-ray computed tomography and CT scanners. And this has become very conventional now. You can see many X-ray CT scanners in different laboratories. So you basically can scan a sample without destroying it. You could basically look inside and you could see the internal structure of that specimen, and then you could do quite a lot of visualization and also quantitative analysis of what is happening. On the right, I'm also including an image of a synchrotron facility. This is the UK synchrotron, the diamond light source. The difference between these two, using these two, would be mainly the rate at which you can grab a 3D image. So benchtop scanners are now catching up, but for now, it's the best solution for really following dynamic processes. If you need the time resolution, is to go and conduct an experiment at a synchrotron facility. But the technique remains the same. You have a sample, you basically have a rotary table, you put the sample on the rotary table, you have an X-ray source, and you have a detector. So during the scan, you basically produce hundreds, sometimes thousands of projections. Like, for instance, this is a projection of basically this, what you probably are familiar with and have seen when you go to the dentist, a set of teeth. And you take quite a few of these, hundreds or thousands of these, from different angles, and you can then put them together using algorithms that are now well developed, and you can create a 3D image of the object that you are studying. Then based on that image, you could basically create quite a lot of visualization, as I have done here, but also you could look at those images and you could basically try to study those images quantitatively. There's quite a lot of information in those images that you can extract, and from that, if you have a sequence of images during a process that is dynamic, you could learn quite a lot from that process. So here I've just showed that the image is actually a matrix of numbers. You could then try to basically isolate a specific phase if you're interested in a specific understanding how a specific phase is evolving. So for instance, here I have been interested in the pore space that is shown in red, that is in between the grains of this sand sample. And you could basically isolate that or segment that phase. But also if you want to take it further and you want to really understand what happens to a single object, you could do that as well. You could, for instance, isolate a specific grain or a specific pore and do all sorts of measurements and try to use that to basically understand what happens during the process that you're studying. So that's just a brief introduction of the technique.
Can I just interrupt you quickly?
Yes.
For a question about the introduction. So you mentioned the tabletop setups and the large scale facilities, right? And you said that the costs have been increasing quite a lot recently. So just like generally speaking, would you say that the tabletops from today, are they somewhat equivalent to the large scale facilities, temporal resolution of how many years ago?
Yeah, we are getting there. This is a very good question. Yeah, this is a very good question. We are getting there in terms of time resolution. In terms of a spatial resolution, of how the fine details that you want to see on your sample, these are comparable. So you can get to resolutions to down to, for instance, in the context that we are discussing. So resolutions of about 1 micrometer or so are very much sufficient for what I am studying here. And you could achieve that using a desktop CT scanner easily. But of course, you need to use a small sample. So that limitation always remains, that to achieve a high resolution, you have to have a very small sample. So millimeter size to achieve micrometer resolution. But in terms of time resolution at the minute, not all of those facilities that are available everywhere in most labs can do a good job in terms of faster scanning. There are new machines, new benchtop CT scanners that are coming, and each one of them are a little bit better in terms of the speed of scanning. So we are approaching to having really fast scans. So if you want, you can have a look at studies that are done by University of Ghent and the equipment, the scanners that they are designing specifically. But we are approaching, but for the moment, synchrotron is the solution in terms of achieving really high time resolution. If you want to scan your sample fast and if you want to follow a really dynamic process. Is that what you meant?
Exactly. Yes, it is. Yeah, I was thinking exactly about the group you mentioned, the group in Ghent. They have quite a lot of these tabletop scanners with several different sources to like
arrangements and yes, yeah. So we are getting there.
Do people feel like in I don't know, 5 to 10 years these tabletop scanners will replace the large facilities, or the large facilities have a long future? Are they safe?
Yeah, so that's a discussion that is a very valid discussion. It is happening, and the development is actually incredible. What we can now do for the type of studies that we are interested in this context. I'm guessing in the next 5 to 10 years we are going to pretty much be able to do everything. But yeah, let's see. But you could do other things in a synchrotron. Sometimes you can actually collect other information at the same time. You have other types of detectors, so you can, for instance, collect chemical composition. So, for instance, the one I know there are plans for the one in Brazil and at Diamond as well, if I'm not mistaken. You can at the same time collect chemical information of your sample, and that especially for cases where you have a reaction happening, like the second case study that I'm going to show, and things are evolving in terms of chemical composition. That would be a really good additional piece of information to integrate into the study. So there are other things that they synchrotrons are still capable of doing that are much better than a bog standard CT scanner. But yeah, okay. So that's that. I think yeah. So this brings us to the start of my first case study. And this is where we started looking at using nanoparticles, non-reactive, and to try to see if use of specific nanoparticle, silica nanoparticle we chose in the end, is going to help us improve displacement of an organic phase, an oil substance from porous media. So in that sense, we were looking at using particles as surfactants. And we know from the past, for instance, there is quite a lot of literature in around oil and gas and improved and enhanced oil recovery, where you use surfactants to try to reduce the interfacial tension. And by doing so, you would basically ease the trapping and overcome the capillary trapping and basically produce more oil. So in this study, we wanted to see if particles can also be used as surfactants. We know from just studying outside the context of porous media that particles, when they are basically included in an aqueous solution and there's a fluid-fluid interface, they basically are attracted to the interface. And this is motivated by a reduction in the total energy of the system. And they basically position themselves at the interface. And by doing that, they are able to reduce the interfacial tension. So if that's the case, we wanted to see if that has an impact on how fluid displacement happens and how fluid basically is organized or reorganized within porous media. So the hypothesis was that we wanted to see if nanoparticles, non-reactive ones, are going to be helpful in terms of overcoming capillary trapping. But when you're talking about nanotechnology and nanoparticles, especially, you have a wide range of parameters to think about when designing an experiment. So you can think about, for instance, nanoparticle type, its size, the concentration of the suspension that you're going to use, the properties, if you're going to use, for instance, a coated nanoparticle, which has a different designed wetting properties, or in general, just bulk particles of the nanoparticle. You can also think about basically the environment that the particles are going to be suspended. And depending on what the application is, you'd end up basically selecting a specific set of a combination of these parameters. So I've included here a few tables. These show what has been studied in the literature more frequently than the others. So silica, alumina, other nanoparticles have been used, sometimes coated, sometimes bare. In this study, we went for bare nanoparticles, so hydrophilic nanoparticles of silica and 30 nanometer diameter. So the setup that we used, you can see the design here. This CT scanner is located at Edinburgh University, and we used a carbonate core plug from basically, this was a multi-scale porosity carbonate rock that we had studied in the past, so we knew quite a lot about it. So we had a core plug of that. This is 1/2 inch size, so 12.5 millimeters diameter. So relative to what you have seen in other studies, and my next case study, this is a relatively large sample that we studied. So what we did was that we had a core plug and we used an X-ray transparent core holder. It's a simple design. It works for low pressure systems, and the details of it is published in an SPE contribution. If you're interested, you could follow that. But it's a simple and nice design. It works very well because it's highly X-ray transparent. So to do this, we had a core plug. We basically encapsulated this in resin, and we basically had 2 end pieces that were all assembled. Everything was assembled together using nylon rods. So everything was highly X-ray transparent. So we put that core holder on the rotary table of the X-ray machine, and we had a pump injecting fluids, producing fluids, and in a specific sequence. And at the end of each injection step, we had a 3D scan of the cell. So the injection scans, the injection steps are summarized here. So in the beginning, we had an oil injection, and then we had the water injection. Then we basically, this is the initial point where you have some droplets of oil or clusters of oil trapped in your system. Then we targeted those trapped clusters by using a nanoparticle suspension. We used two different concentrations, and we wanted to understand if making it different, increasing the concentration would make a difference. So we used a low concentration and a high concentration suspension of silicon nanoparticles. So as just we discussed, the question is relevant because we knew that the time resolution that we were achieving, about half an hour or so for a 3D image, is actually not enough to see the dynamics of what was happening in this process. So in order to collect more data and more information, we decided that during each injection step, we're going to collect thousands of 2D projections. So obviously from those 2D projections, you won't be able to go and reconstruct a 3D image, but as it turns out, and I'm going to show, you can actually have quite a lot of understanding established based on those 2D projections, the shadows of the cell on the camera. So we did that. So the data set is a number of these 3D images at the end of each injection step, but a number of sequences of images that were captured during the injection steps. I'm also here showing you the pore throat size distribution for this specific rock. And I just want to highlight that the peak is between 10 to 20 micrometers. So we were not particularly bothered about having the particles basically mechanically filtered at pore throats because particles are quite small. So here I'm just going to present the outcomes. So I'm skipping all the details of what we did. But here I'm showing you the saturation, the oil saturation after each injection step. And this is all calculated based on the 3D images. So, and this is for the field of view that we had. So this was only part of the core, not the entire core. So as you can see here in the beginning, after the oil injection, we had about 78% oil in the core. Then we basically had the water flooding. So the imbibition step, water came in, removed quite a lot of the oil, displaced that. So the remaining oil, so this is the target, the remaining oil is about 41%. Then we followed that with the lower concentration nanoparticle injection and the higher concentration nanoparticle injection. Flow is happening very slowly. Everything is capillary dominated. However, what we were expecting was to see at least some change in the total amount of oil that was remaining in the core, but that didn't happen. So if you look at the oil saturation, it's not moving at all. So we thought about this and we basically asked ourselves this question: if this is the case, is it really worthwhile planning and performing a nanofluid injection, given that it involves quite a lot of cost and planning and everything? Is it worthwhile doing this if it's not really impacting the overall oil saturation that is remaining in the column? So if you are judging just based on looking at the images that were collected at the end of each step, you probably would say no. But what if you had a tool like we had to look at what was happening during the course of the flow? And we also had a look at we also tried to compare the different injection steps. So here I'm going to show you the oil saturation right after the oil injection. So this is the green line, and you can see this is about 70% throughout the column. So this is along the length of the core, so going about 70 odd. And then we injected the water, so it dropped the saturation down to around 40 odd. And then we injected the lower concentration, higher concentration nanoparticles, and you can see these are all very much tied together. I've tried to basically show this in a better way by trying to remove the saturation of oil after water flooding from these 2 nanoparticle injections. This is just a simple subtraction. And what you can see is that for the low concentration nanoparticle injection, the line, which is the red line here, is basically fluctuating around 0. So there's not a lot of difference between the low concentration nanoparticle injection and the water flooding. But as you can see here, there is quite a lot of local differences, local movements that you can spot here for the higher concentration nanoparticle injection. So we also looked at a 3D image of basically only the oil phase here displaced, all the displacements that were happening at pore scale. And we can see that after the low concentration nanoparticle injection, not much is, again, there are some displacements, but more substantially is what we could observe after the higher concentration nanoparticle injection. And this is basically this, what you can see in color put in numbers. So what is happening at after the higher concentration nanoparticle injection is quite a lot more substantial. So we wanted to now go back and look at those sequence of 2D projections and see what's happened. So to do that, the first thing that I did was to remove the image of the rock, just the projection of the rock itself from the sequences that we had. This enhanced the contrast between the fluid phases. So here you have a sequence of images, say for instance 2000 to 3000 projection of those images. So this is the core holder that has fluids in it, and you're injecting the fluid and you're taking snapshots. You're not rotating the sample, it's staying at the same place. You're just collecting thousands of projections to try and see if you can basically understand anything about the dynamics from those 2-dimensional projections. So what we did, and I think this was this made the study interesting, was that we started to look at the data in a slightly different way, and specifically we try to reslice the images, the projections that we had in time direction. So by doing that, so if that's a slice, so if you look at the bottom image, you can see that basically on a shadow on the detector, every slice through the object is represented by a line on the detector. Okay, so if you then take this re-slicing, what you're seeing is an image like this, and that image represents what happens to that line of the detector over time. So if there's fluid movements going into that line and going out of that line, you're able to see that using this re-sliced image. So that's just an example of a line just halfway through, middle of the detector. And you can see that by doing this reslicing, we notice that there's quite a lot of movements of droplets, oil droplets. So oil is now shown in the darker phase. So oil is moving in and out of that line in different areas of that basically slice of that one line in the detector. So, and this was after the nanoparticle injection with the high concentration. So we noticed that this data is actually able to show us this sort of dynamics. So we went ahead and applied that to all of the sequences that we had collected during the injections. So if you do that, this might look like a little bit busy, but I'm just trying to hopefully explain it in a simple way. So what we have here is that we have a re-sliced image. So each one of these is a re-sliced image of a row. So for instance, a row, just imagine a row on the detector. So this is the beginning of the pore, so the beginning, the inlet phase of the core. So the last one is the outlet phase, and these two middle ones are two rows in the middle on the detector. And what you can see is that you have these different injection steps. So in the beginning, the first row is the water injection, then we have the nanoparticle injection, low concentration, nanoparticle injection, high concentration. So what we can see, and in order to make this a little bit easier, I also plotted the signals. So this is just a line profile through these images that you can see down here. So what you can see here is that in the beginning, during the water injection step, the signal actually shows a clear jump, and this is what we expect because we have basically observed about 30% oil removal from the field of view. So we expected the signal to actually show this. So this comes very clearly, is captured, so the signal jumps, all of that oil is removed from the pore space. What you can also see is that basically for about 100 minutes, so this is this yellow box, 100 minutes at the end of this water injection, nothing is happening, not much is happening. So you're injecting water, multiple pore volumes, injecting water, there's no special movement being detected. And this basically reflects that everything else that is in there is actually trapped under capillary forces. You're not going to produce that trapped oil if you're not changing one of the parameters of the system. So then we look at the low concentration nanoparticle injection. It's this middle section. It's not showing a lot of dynamics apart from this random droplet that is moving. But when you look at the higher concentration nanoparticle injection, you can see that there's quite a lot of dynamics that are being captured. So you can see the droplets are moving in and out at different points in the core. All over the core, you can actually see that there is movements, fluid movements that you have. If you didn't have this, you would basically miss all of that movement and all of that dynamics. So overall, by looking at this plot, you can see that this higher concentration has actually been able to create that environment and ease that capillary trapping. So we then looked back at the 3D images and we were looking for evidence and signs of what is going on, what's happened to the oil structure as a result of these movements that we were detecting. So there's quite a lot of movement. So what's happened? We realized that actually this existence of this nanoparticle has induced formation of an oil in water emulsion. So I'm here showing you some examples of these emulsions. These are actually the actual grayscale images that we took. So this is the brighter phase, is here the oil phase. So you can see that there are droplets that are formed. And because we have nanoparticles in this system, the nanoparticles sitting at the interface, oil-water interface, actually also stabilizes those droplets. So they're not easily joined together. So that's what we observed. What we also quantitatively were able to measure was that as a result of that, the surface area of this droplets the oil phase in general has increased quite substantially during the higher concentration nanoparticle injection. So where you see that there's comparable surface area for the lower concentration and the water injection. In contrast, for the higher concentration nanoparticle, you see about 2 times surface area for the oil phase. And that goes hand in hand with the number of clusters, number of droplets that we observed that are quite a lot more compared to the water injection and the lower concentration nanoparticle. So you have quite a very different distribution in terms of the shape and the structure of the oil phase in porous media. And if you were thinking about degrading this oil phase in situ, the surface area is an important parameter to look at because that's where the contact happens and the reaction happens. Okay, so I want to wrap this up because I want to move on to our second case study. So in this case,
can I ask a question?
Yes.
I have a question regarding the previous slide. As we know, if the oil clusters join together, we expect them to do some sort of banking before the production, and in the banking scenario, we expect a lower surface area between oil and water. Okay. Am I missing something or I'm mistaken? Because you have said after you have injected the nanoparticles, the surface area between oil and water have been increased, which means more smaller droplets, not less bigger droplets of oil.
Yes, that's what I'm saying. So first of all,
how does it help us in entrapment or in remobilization of the oil phase if it's going to break the oil ganglia into smaller clusters?
okay. So just to be specific here, before I mention, I respond to a question. Here I'm showing the normalized surface area. So I'm taking the surface area and dividing it by the total volume of the oil. So it's all comparable. So that's one point to look at. But in general, this is what we observed. So we injected the nanoparticles and we collected an image. On the image, we see that there are quite a lot of many more, and this is measured here, how many more smaller droplets that are confined within the pore space, where we had larger droplets in the past, before the injection had happened. Now, in terms of how this might help or not help, obviously this is a discussion. The main discussion and I have thought about this myself, the main discussion is what would be the implication of having smaller droplets and an emulsion on the viscosity of the fluid phase that you're trying to displace. And it's a more complicated discussion because it also depends on what type of emulsion you have. If you have an oil in water emulsion, the implication for viscosity is going to be different from water in oil emulsion. In another study, we've seen formation of water in oil emulsion, and that makes the viscosity really a lot. It increases the viscosity quite substantially. Whereas if you have, for instance, heavy oil situation where you are trying to produce the remaining heavy oil, and you are able to induce producing an emulsion phase, this might help you reduce the viscosity. So in that sense, you might be able to produce some more of that oil by actually inducing having an oil in water emulsion. So I don't know if that answers any of your questions or it makes more sense.
Yeah. It makes sense. But yeah, it's a place of discussion, to be honest, because we should see. You did maybe I missed this part, but you didn't show the overall saturation of the non-wetting phase during the course of the injection to see if the saturation is overall increased or decreased.
Yeah, this is what I showed in the beginning. It's not changing.
It's not changing, it's just redistributing.
It is redistributed.
Yeah, exactly. But we should see if it is not changing and injection of nanoparticles is breaking our ganglia into a smaller sizes. I wonder if it will be helpful to produce the non-wetting phase. So yeah, it's a place of discussion. Thank you.
Thank you for your question.
No worries.
I did try to stop myself going into details, but there's quite a lot of discussion around this. One thing to keep in mind is that, as I mentioned, we are only looking at a small section, probably about half of the core, and in the middle. So this section has a section before it and a section after it. So what you're seeing is not the whole of the column. So one of the possibilities is that there's, and this is what we're showing, is that there's quite a lot of fluid moving in and moving out. So it's not just, the fluid is not being redistributed inside, but there is this link with the sections that you are not seeing. What we are showing here is that there is dynamics that is happening. And the second thing that I would say, and I'm really conscious of time, is that if I go back, it's here. So at the pore throats, if you manage to establish a lower interfacial tension, you are able to create droplets that are smaller. So this is just based on having interfacial tension, and if you reduce that interfacial tension, the snap-off happens quicker. So you are going to end up having smaller droplets. Now, if you have particles that can then sit at the surface of those droplets and make those droplets that you've formed a little bit stable, then you will end up having a scenario like what we have, in which you're actually observing formation of droplets that are happily sitting together. And we had images of this after a few days as well. They were happily sitting together without actually joining and creating larger droplets. So we need to consider all of those all impact of having particles and interfacial tension sitting at the surface. I can see that you've put a thumbs up. So happy that you're at least relatively satisfied.
I didn't want to I just wanted to say, it's good. Thank you for your explanation.
You're welcome. Okay, because I've been thinking about all of these myself. So very valid questions. Okay. Just to wrap up this case study that we had, we showed that if you use nanoparticles, you are able to influence the structure of the remaining oil, possibly overcome the capillary forces, redistribute the remaining phase, and that could contribute towards actually improving the recovery of that phase, removal of that phase. Or if you are thinking about degrading the phase at a later stage, you'll have a different structure for that fluid phase. We also showed that using 2D radiograms and capturing thousands of those during the injection steps are actually quite useful in capturing some of the dynamics that you would otherwise miss. I just want to mention here that what I'm showing here is different from another pore-scale mechanism that we observed about 5-6 years ago. That we named it as droplet fragmentation, and that happened in the same rock, but the experiment was different. We didn't have any nanoparticles in that case, but we had injections at using two different flow rates and at two different flow regimes, capillary dominated and viscous dominated. And what we showed in that study was that droplet fragmentation happens as a result of moving from capillary dominated to viscous dominated, and especially because we had this multi-scale carbonate rock. So it's not that, I just wanted to make this clear, but if you're interested, you could read that paper as well. Okay, so moving on, this second case study is a study that I've been doing with partners from Brazil and Italy for the past 4 or 5 years. And in this study, we are looking at using reactive nanoparticles, and the application is groundwater remediation. Okay, so specifically, we are looking at a family of contaminants that are called chlorinated solvents. These I have included the chemical structure for you here, and these are one of the most persistent contaminants out there. And synthetic contaminants, man-made, we've used them for many years in a range of industries. They're really nice solvents in terms of properties. As a good solvent, they're really powerful. And we didn't know when we started many decades ago using these in industry, we didn't know that they actually have quite a lot of health implications. For instance, they can cause kidney and liver damage. Some of them are actually carcinogenic. I've actually seen people who have been exposed to this and later on have been diagnosed with cancer. So these are really significant problems and global problem, because they have been used in many countries over many decades. Now we don't use them anymore, so we recognize the fact that they should not be used at this scale. But the damage is already done. There's quite a lot of these already subsurface contaminating groundwater, and basically the idea behind this study was to try to see if we can, from pore-scale perspective, look at some of the new technologies that are targeting in-situ degradation of these contamination. So in the past, conventionally, if you have a leakage at the surface, so the problem starts like this, that you have a leakage at the surface of this contamination. These are denser than water, so they start to penetrate through layers layers just beneath that contamination, the release source, and they would keep going until they actually hit an impermeable barrier, and they basically create a source of contamination in that area. And groundwater has a natural flow to it. So it basically starts to create a larger contaminated area around that source, which we call the plume of contamination. If you think of how soluble these chemicals are in water, it's not that the solubility is very poor. So you're looking at grams per liter in terms of solubility. So if you were thinking about washing this contamination source with water, you're going to look at investing quite a lot of energy and using a lot of water, producing a lot of wastewater. So not really sustainable. But also, if you think about the levels of this contamination, the maximum level you can have and still be able to drink this water, this is around micrograms per liter scale. So, this means that a small amount of these can actually render quite a large volume of water unsuitable for drinking. So we need a technology or a suite of technologies where you can actually deal with the source of contamination, preferably in situ, to basically be able to not disturb what is happening at the surface. A lot of these contaminations are in the backyards of basically small, medium-sized factories. So you don't want to stop all of that production while cleaning the environment if possible. So at pore scale, if you look at the pore scale, it's a very similar story. You have droplets of these oily substances, organic substances that are sitting trapped in between the grains of, in most cases, sandy environment. So the idea here is to try to, again, target those remaining residual phase and try to, in this case, if we can, degrade those in situ, turn them into something that is not that harmful in situ without actually having to bring them up to the surface. So that's the problem. In recent years, there has been quite a lot of investment in using nanotechnology to do this. So specifically, we are looking at using reactive nanoparticles. So for this case, zero valent iron nanoparticles. So this is a very reactive nanoparticle. It's iron kept at zero valent. And if you basically mix this, create a suspension and inject it subsurface, as soon as it comes into contact with the chlorinated solvent, it starts to go through this chemical reaction, promotes this reaction, and it basically produces a hydrocarbon, just like this reaction is suggesting, which basically, if you look at it, is a gas phase. So when we looked at this reaction, we realized that actually you're doing a reaction. This is a chemical reaction that is happening, and off the back of that, you're actually producing a gas phase, substantial amounts of gas phase, and that gas phase can actually start to now redistribute the arrangement of fluids, and potentially it can basically start to help us overcoming the capillary trapping for the droplets of this contamination that are stored. Maybe it is going to be helpful in terms of remobilizing those droplets. So that's the idea behind this case study that we did. We had a similar setup. We had a column. This time we had a smaller column. The pore space is a bead pack, glass bead pack. We had, for the contamination, we had trichloroethylene. It's one of the main chlorinated solvents that is causing problem. And for the nanoparticle suspension, we basically had this suspended in water, and it was the size of the particle was about 50 nanometer. So the experiment is similar. We had this column on the rotary table, installed on the rotary table. We had injection pumps, and during the injections, because we did this at the synchrotron facility, this was done at the Brazilian synchrotron, we were able to actually capture some of that dynamic during the course of the injections. So what we did was that we started off by starting by basically saturating the core with water. We injected the TCE phase. So this is the contaminant phase. I'm going to refer to it as TCE, trichloroethylene. We injected that. Then we pushed all of the mobile TCE out using an imbibition step, so water injected for many pore volumes to try to basically displace all of the mobile TCE. And then after that, we are now having droplets that are not moving. These are the source of contamination. So we injected nanoparticle suspension. We did this using a different pump because it had its own challenges. It was not easy. Okay, by doing that, we did the nanoparticle injection in 2 steps. Each of these two steps were separated by 6 hours, and this is just to mimic what's happening in the field where people apply more than one cycle of nanoparticles. Okay, so this is a picture of our setup. This is the column that is somewhere up there, and all the pumps that we had and all the fittings and everything that we had, and half of the team obviously happy. This is just at the very end of this experiment, and this is at the IMX beamline of the Brazilian synchrotron. So I'm now jumping and showing you the results of the experiment. So here in red, you can see the contaminant phase, the TCE phase. And on the bottom left, you can see the time at which these images were taken. So time resolution about 6 minutes. We can still do better in other places. This is the best we could achieve there in Brazil. So what you can see is that in the beginning, we have about 12%. So that's the saturation of TCE in the bit that we were imaging. So again, this is smaller than the whole column. So we had 12% to begin with. We injected the nanoparticle first time. We haven't seen so you're not actually seeing the nanoparticle suspension phase here because it would be very busy if I show all the phases. I am only showing the TCE phase, which is what we are interested in removing. And at a later stage, you can see that the gas phase is shown in yellow. So in the beginning, we have 12%. We injected the nanoparticle phase. We don't actually observe the nanoparticle until this stage, until time equal to 119 minutes. But just injection of the nanoparticle phase actually reduces the TC saturation down to 6%. So this is because the nanoparticle phase was more viscous. So this is some viscous dominated displacement. But what we can also see is that gradually we can start to see that there is formation, and later by the second nanoparticle injection, flow of a substantial amount of gas into the part of the column that we are imaging. And that is also coupling and reflected in the pressure response that we were collecting. So the first hump is to do with injecting the nanoparticle for the first time. And for the second time when we inject it, and when there's quite a lot of gas in the system, you can see quite a lot of instabilities in the recorded pressure, because obviously pressure is a compressible fluid, and you get to see fluctuations in the recorded pressure. Okay, so this formation and flow of gas is a mechanism that we can see at larger scale is happening in the entire part of the column that we are looking. So it's overall happening everywhere, but we wanted to see how effective that is. Now, if you look at the concentration of TCE, after we have the flow of gas everywhere in the column, the concentration of TCE is reduced down to 2%. So we're going from 12 to 6 and now reduced to 2%, which is quite substantial in terms of eliminating, moving those trapped droplets that I mentioned in the beginning. So this is quite interesting for us. We wanted to now go back and see and explore what is happening at pore scale. So at pore scale, what you can see is that we identified 2 main mechanisms that are contributing to all of the dynamics that I showed you. So the first one is the gas formation and flow. And the second one is that we actually noticed there are some chemical reactions and evidence of degradation that is happening at the interface of the contaminant phase and the nanoparticle phase. But this is a much slower process, which I will show in a bit. So the first one is displacement directly by the gas phase. And here I'm showing you two examples, so 3D rendering, but also here I'm showing you examples, the same examples here, but the grayscale actual slices through the actual data that we have collected. So here what you can see is that we have a droplet that is basically sitting in the porous space after the water injection. This is trapped. This is under capillary forces trapped. It's not moving. This is after the first nanoparticle injection. It again is not moving due to the viscous dominated flow that is happening here. This is the other higher viscosity of the injection fluid. So it's totally trapped. What you can see is that as the gas is coming in, because gas is a non-wetting phase, it preferentially wants to occupy the center of the pores, and hence it basically pushes the TCE phase out from the pores that were confining it. So here I can show that I can basically take you through the sequence on the slices. So here we have the TCE droplet. You can see the beads. These are the round objects here, and you can see water that is in the darker phase. So here after water injection, some of that cluster that was trapped is now remaining. So this is the target of our study. We want to remove that trapped oil or trapped solvent here. So we injected the nanoparticle. Nanoparticle is this sparkly phase that you can see probably on your screen. And what you can see, that nanoparticle comes in, it doesn't displace, it doesn't move the trapped TCE phase. But when gas comes, after the reaction happens, and when gas comes into play, it basically is able to shift that TCE phase outside the pore that was confining it and was trapping it. And it's the same story here. You've got a TCE cluster here, it's not moving, and gas comes in and pushes it out. Here you can see this quantitatively. So I'm showing you just the amount of TCE that we have in these two boxes. And as a result of this gas coming in, the amount of trapped TCE drops quite significantly and quite sharply. Overall, when you look at everything in the box that we imaged in the field of view, we had 57% reduction in TCE saturation, which is quite substantial. The second thing that we observed was that for some of these droplets, and I'm showing you the 3D renderings here, but a slice through that in the bottom, what you can see that there are some TCE droplets that are trapped. They're not pushed out using the nanoparticle injection for the first time, nor they are being affected by the second nanoparticle injection in terms of they probably are not in the pathway that gas has chosen. So they are staying intact. And what we saw, and this is after we left the reaction to happen overnight and after we came back next day, so this is quite some time later, what we saw that there is an actual reaction that is happening, and the TCE droplet is actually being degraded directly at the interface that it has with the nanoparticle phase. So for this case, you can see that this decrease in the volume of TCE is a lot more gradual. So here for this case, it's about 13% reduction over 1 day. But nevertheless, it is happening. So, and that's the target of this technology. It wants to target remaining droplets that are trapped, and it wants to degrade them. And that's what is happening here. And this is the first time this has been, all of this actually, the nano remediation has always been applied at the field. They basically calculate how much nanoparticles are required, and then based on an estimation of how much contaminant we have in place, and then they inject and they basically monitor what's going out. But at small scale, at pore scale, none of this has been looked into before this work. So we were really happy to see all of that. Okay, so one of the last things that I want to show you is that we also thought about what would be the impact of having this much gas in our system on spreading of contaminated water. If you remember in the beginning, I mentioned that there is a source of contamination that has residual droplets, but also there is a wider range of contaminated area that we call the plume of contamination. And we thought that if we are producing a significant amount of gas, this gas might actually occupy the pore system, act as a cushion, and reduce the relative permeability, and would basically help with stopping the spread of contaminated water. And we wanted to see if this is happening. In order to do this, we only looked at the water phase after all of these injection steps, and we used the image, the binary image of the water phase, and we performed a wettability measurement using Navier-Stokes equation. If you do that, and if you plot the water permeability, this is now shown in black. So this is water permeability. What we observed was that obviously water permeability dropped as the first nanoparticle injection happened, but more significantly, it dropped from 60%, dropped to less than 1% as the gas came in, as the amount of gas that was being formed as a result of this reaction was actually it was formed, and it was mobile, and it was occupying all the pore bodies. So this is an added benefit, because you're trying to facilitate the reaction, but at the same time, this is helping you in stopping the contamination to go further. So this is an added benefit to this technology. Okay, so after that experiment, we thought that we want to repeat the experiment, but this time, hopefully at a higher time resolution, as well as using a larger sample and a more representative sample. So we took the experiment to the diamond light source, and we performed a similar experiment, similar steps. And this time we used a sand pack instead of glass bead pack, and you could see an image here. This is obviously the team at Diamond, very happy. And we actually produced quite a lot of data, more than 60 terabytes of data in 4 days. So we haven't yet looked into the data. I've got just slices through the data to show you. But what we saw, so this is a slice through one of the columns that we used. So obviously the advantage here was that Diamond had a higher energy range, so we can use a larger sample. So we used more than twice the size of the column that we had. We used a natural sand sample. We had studied the sand sample in several other studies. So we had a very good knowledge of nanoparticle filtration and all of that through this sand column. So this was a really nice choice to add to all of that understanding. And it also provided us the imaging, and the higher energy provided us with a better data set in terms of the contrast between the phases that we captured. And we also we went down to time resolution less than 1 minute, and we weren't actually pushing the beamline. We could have gone faster, but we realized that in terms of then looking at the data, this would be a crazy amount of data. So we thought we settle for that less than 1 minute time resolution. Okay, so here you can see obviously just a slice. You can see that we can see on this slide the sand particles. We can see the nanoparticle phase. So this is the sparkly phase. We can see the TCE phase, the contamination phase. So all of this is very much clearly captured. What we could see just by looking at the slices as we were producing the slices was that the two main mechanisms that we had identified based on our previous data set and published are actually there. So we could see formation and flow of gas. We could see that gas bubbles are pushing into pores, which originally basically contain the TCE phase. So by doing that, they are changing the distribution and shape of the TCE clusters, the contamination cluster. And we could see quite a lot of other interesting stuff. So in one of the experiments, we also observed that we can actually, with the time resolution, we could see the settlement of nanoparticles in one single pore. And that's one of the challenges that injecting nanoparticles subsurface has, that you get to filter quite a lot of it in some cases. So we haven't yet actually gone through the data, as I mentioned. So I just wanted to show you just a glimpse of what we have. We are very excited to look at that data. So to summarize, I have tried to make a case for using nanoparticles in subsurface to try to look at impacting capillary trapping for different purposes, reactive and non-reactive nanoparticles in these two different case studies. Final point that I want to make is that we have published all of this data. So these are all made public, so you can access the data set, you can download the data set and work on the data set, apart from the diamond, which we haven't yet worked on. But for the two case studies that I presented, both of them are published. You can access directly the data set, and you can download the data and work with it if you wish to do that. So I just wanted to quickly show how you can do that. And that's my last. So for the first case study, we basically published the data as a paper in scientific data. This was actually, we were invited by the editor to publish the data because the data was in itself interesting. So if you go just access the scientific data paper that we've published, you could basically find the link to where the data is deposited. So I'm just trying to find that now. So the data is deposited on the Figshare repository, and you can basically just download the data, and there's a data descriptor. So the paper is the data descriptor. So it describes what the data is in great extent. So you basically will be able to understand the data and hopefully use it. So that's all. Thank you very much for listening to me. I have been very happy to do this today.
All right, thank you very much, Dr. Pak, for this presentation.
Yeah.
Do we have some questions?
I think all the questions were asked during the presentation, which is a style that I actually like. So it allows an actual interactive discussion.
I think we have some questions already there. Maybe Don, people are raising the hand.
Yeah, can I ask a question?
Sure.
I came with a lot of questions actually. Thank you so much for your presentation.
You're welcome.
I have a question regarding how you conducted the experiments. Did you have a back pressure for your microcore? Because we had this experience in diamond light source that if we didn't have a back pressure, we could generate some water evaporation by when X-ray hits the core. So I wanted to know, how did you make sure that this gas is produced due to the reaction, not the X-ray injection?
Yes, very relevant question. This was our main concern in designing the experiment. We knew that we wouldn't have this problem in IMX because the range of energy is low there. So this wasn't going to happen at IMX in Brazil.
I think you were in I11 or I12 beamline in diamond, am I right?
I12.
Yeah, I12. Yeah, we had the same issue there actually. I want to know, how did you make sure? Yeah.
So we actually we were thinking about using a back pressure all the way through, but it's not easy to use a back pressure when you have nanoparticle suspension coming through. You are going to filter all of those particles, and you're going to clog the back pressure regulator.
Yeah.
So it's not, so we thought about it long and hard, but in the end, we decided that we are going to use a lower range of energy, and that helped us eliminate the bubble formation. We knew this bubble formation exists. So
Okay.
we did quite a number of scans in the beginning to try to check if bubble is forming without the nanoparticle, obviously, just water and and the oil phase
I
later.
think using a lower range of X-ray, it makes your life hard actually for your fluid segmentation actually.
Yeah, so it's a balance that you have to hit.
Yeah, true.
So and you wouldn't know for the sample that you are using unless you actually try how the image would look like for the phases, using the image that using the sample size. So there is a link between the sample size, the resolution you are trying to achieve, the field of view that you are targeting, and the phases that you are basically injecting, and how much doping you're using. So how much X-ray absorption you are putting on the way of X-ray.
Thank you for your answer.
So
another question.
Combination.
I'm just curious. Do you know how the X-ray does it accelerate the reaction between nanoparticle and the contamination? Because if this is the case, it cannot be easily extended to the fields because you are somehow catalyzing or accelerating the reaction between nanoparticle and your contamination with the X-ray actually.
I don't know if the effect exists, to be honest.
Okay.
I don't know, and I don't know how we may be able to measure this. We probably will.
And did you have any salinity in your water?
No.
I wonder how the existence of salinity and redox environment changes the performance of nanoparticles.
This is another relevant design parameter that we had to think about. Okay. If you think about actual subsurface groundwater systems, there is a natural ionic strength and contribution from different ions that are naturally found in groundwater systems.
Yeah, but you have used the ionized water.
For now, we have used the ionized water in this study.
Okay.
But we have other studies where we are looking at only the filtration of how nanoparticles move in porous media, because these nanoparticles are very, it's a challenge to actually get them to move through porous media. So in other studies that we're conducting, we are not looking at the reaction, but we're looking at different environments and how having different environments like different salinity and different ionic strength would impact the mobility of nanoparticles in porous media. To make it a bit more relevant to what's happening at the field.
Yeah, thank you. Thank you so much for your answer.
You're welcome. Thank you for your very nice and relevant questions as
well.
My
pleasure. Thank you.
I think we also have a question from Marcel.
Sure.
Yes, but maybe Francois could ask first. I think maybe Francois left, right? All right. So I can ask away. I have many questions. I'll just ask a quick one, and maybe I can drop you a message later or because this is obviously very interesting to many of us. We're bothering you, interrupting you all the time. So
no, I'm here for this, so I'm very happy to listen to you.
And I think you did a very good job at making this understandable for those of us who are not experts in the field myself. So thank you very much. A quick one. So you showed two separate works, and in the first one you had like this emulsification and making big clusters turning into small ones, and the other one you had like the reaction part with formation of the gas and so on. So could these two things be combined to enhance the effect? Is it possible?
Yes. You can do anything because you're designing this. If you're thinking about coming up with a more clever way of basically overcoming capillary trapping at field scale, you could really do anything. But when it comes to actually applying it at larger scale, there are a number of factors that come into play. For instance, what is the cost of doing this? So if you're thinking about injecting this nanoparticle first and then another nanoparticle, and you're combining all the costs and the campaigns that you need to have, the time of injecting these in a sequence. So typically a simpler scenario would be more favorable because you're applying it at larger scale. But what we thought was that perhaps you could think about having, for instance, just a simple soil water flooding. We call it water flooding, but it's also referred to as soil flushing. You could perhaps think of combining what I presented in the last case with following that with soil flushing, for instance, to try to capture all of those droplets that are now released. What we also thought about, and we have made a note in the paper, is that maybe this is not a good, not an advantageous effect in the end. You don't want to release the contaminants from where they are necessarily. If you think about a contaminated groundwater case, in oil and gas, we think if we move the oil, it's good. It's going to increase the mobility, and hopefully it's going to contribute towards improved recovery. But in contaminated groundwater, it's not always the case that if you move the droplets, the contaminant, the residual phase, you might actually push it into areas where previously were clean. So you might actually, if you don't do this correctly, you might actually end up having a larger area that is now seeing residual phase of contamination. So there is a caveat around all of this, but what we wanted to show was that this is happening if you are inducing a reaction, and that reaction is releasing a lot of gas. At field scale, typically just detecting gas is a very good sign. They basically think, okay, the reaction is happening, so we are doing well. But what we wanted to just highlight is that the gas is happening at the smaller scale within pores. This gas might not do what you think it is doing. It might start to shift the contamination and move it, make it mobile. So you need to think about that as well. So that was the point we were making here.
Thank you.
Okay, you're welcome.
All right, do we have a further question? I think Francois had some left us. I'm sure he can contact you if he wants to ask it. Then if we don't have further question, would like to thank you again for presenting this topic to us today. And thank you to all the participants who have joined us.
Yes, thank you very much. Yeah, it was a pleasure to be here and to meet with all of you. Hopefully in the future we get to meet each other in person at some point.
That's when the travel restrictions are going to be
hopefully
lifted.
With all having the vaccination, hopefully things are settling down. So hopefully we get to maybe in an Interpol conference at some point.
We all wish for it.
Yeah.
So thank you again, and
Same here.
I wish a good night to everybody, or a good day, at least to Marcel.
Yes, have a nice evening to you all. Thank you very much.
Bye-bye.
Bye for now.
Bye.